It so happens that my second name is also Philip, so this is 3 Philip's work. Okay, so ordinal computability is probably not known by everyone in the audience, so I start with a somewhat extended motivation for the area, and I will start this by first considering the role that recursion theory, or a role that recursion theory plays in mathematics. By the Church-Turing thesis, we can get negative results on computability, which allows us to show that certain problems are not effectively solvable. And such results can be quite relevant for mathematics. For example, Hilbert's 10th problem was solved in this way, deciding whether or not there is a particular Diophantine equation has solutions. We know it's not Turing computable, this problem. We have the Church-Turing thesis, which says Turing computability models our intuition of mechanically solvable, so we know it's not mechanically solvable. And there are other interesting mathematical problems, for example, deciding whether an elementary function has an elementary antiderivative, or whether the integral from -infinity to infinity exists, that are also not algorithmically decidable, and therefore we know we don't need to look for a mechanical solution. So what's the contribution of such results? Well, there are at least 2 of them. First, they save us from unsuccessful attempts, and second, they direct our attention towards what we can still achieve. For example, in general, we cannot decide whether Diophantine equations are solvable, but maybe there are special classes for which the problem is decidable. Now, why should we extend computability to the infinite? Well, Turing computations model the idea of computing with integers, but in actual mathematics we handle much more subtle objects, much bigger objects that cannot be coded by integers. And still it seems that the notion of a mechanical manipulation of such objects is meaningful. And also, actually, in mathematics we make quite often use of explicit constructions with infinitary recursive definitions. For example, when we prove things like every field has an algebraic closure, or every reclosed field has an integer part, or when we define the V hierarchy in set theory, or something like this. So proofs given by such explicit procedures are often preferable to indirect proofs, since by the construction method we can investigate the object that we constructed. For example, maybe there is an indirect proof that there is a minimal transitive class model of ZFC, but certainly the recursive definition of L helps a lot in studying L. And this is one motivation why one should study models of infinitary computation, because they give a precise meaning to what it means to be constructible, computable effectively in such a way. So I'm not the first person to investigate such ideas. There is a paper by Wilfried Hodges called On the Effectivity of Some Field Constructions, which starts like this. Since the 1930s, we have known exactly what it is for a function of natural numbers to be effectively or algorithmically computable. Now, every mathematician is at least vaguely aware of another quite different notion of effective function, which has nothing at all to do with enumerable sets. And then he gives some examples, namely the function that takes an integral domain to its field of fractions, f0, and the function f1 that takes a ring with identity to a maximal ideal, and goes on to say, in the sense which concerns us, function f0 is effective, function f1 is highly non-effective. To prove theorems, we have to replace this intuitive notion of effectiveness with something more precise. So this clearly demands a definition for effective procedure in the infinite. And he uses Jensen's and Skarp's primitive recursive set functions. Another idea for the use of infinitary computability is to get negative results on classifiability. There is a nice paper by Garvin Mellus, which is called "One Cannot Show from ZFC that there is an ARM-type classification of the countable torsion-free abelian groups," where we find the following sentence: in order to prove non-classification, we need an exact definition for the intuitive notion of effective construction within set theory. Okay, so I think these are two motivations for studying generalized computability. There are more, for example, there are applications in model theory, and of course there are many other reasons, but I'll take this as my motivation for this talk. However, from a set theoretical point of view, it has often been stated that ordinal computability is a very restrictive point of view because, well, basically every sensible concept of computability is absolute between V and L. So all these machines run in L, and so what they compute is only constructible, and you don't get beyond the constructible universe, which is of course quite restrictive. You don't get beyond the absolute minimum of what there has to be in a model of ZFC. So this phenomenon, let's call it the constructible barrier. Objects that are approachable with notions of infinitary computability seem to belong to L. This is somewhat unfortunate, so there have been repeated requests to come up with a meaningful way of computing beyond L, and the work I'm presenting can be seen as an approach to achieving this. So the model I'm working with are ordinal Turing machines, which were introduced by Peter Köpke. An ordinal Turing machine, software-wise, is the same as a classical Turing machine. Yeah? It's exactly the same notion of program. Every classical Turing program can be run in OTM, and vice versa. So we have just the classical Turing machine commands. I guess you're familiar with them. Also similar to Turing machines, OTMs have a tape that is indexed with ordinals. On the tape cells you have 0 or 1s. You have a read-write head that runs on the tape. You have a finite step of internal states that we enumerate with natural numbers, and possibly you have also an oracle. However, why is it called ordinal machines? Because the indices that you use to index the tape cells is the whole class of ordinals, so you have an ordinal sized tape, and also the running time doesn't stop by omega. You can run into the ordinals as long as you want. So how does that work? How does such a Turing machine compute? Well, if you are the successor ordinal, you just do what the Turing machine would do. Replace the tape content, change your internal state, move. New phenomenon is when you go to a limit time. For example, what should you do at time omega? Well, first of all, you need to determine the internal state, and we just say this is the inferior limit of the earlier internal states. The internal states were indexed by natural numbers, so this makes sense. The head position at a certain time is also the inferior limit of the earlier head positions, which is always possible since we are in the ordinals. Now there is a little subtlety, namely if you are at the limit position at the tape and the instruction tells you go to the left, what do? Well, in this case you let the head jump back to the start of the tape. And concerning the tape contents of a certain cell, you look at all earlier tape contents of that cell, and then you take the inferior limit. So if there were cofinally many zeros, it's 0, otherwise it is 1. Okay, and we further distinguish two variants. There's a parameter-free OTM that starts on a tape which only contains zeros on cells with the infinite index. Possibly there's a real input. And for a parameter OTM, you are allowed to mark one particular cell with a 1. So for example, you may tell the machine what omega 1 is, or so. Okay. So I take it that you understand how an OTM works. You just carry out these commands. We call a function from the natural numbers to the natural numbers, very canonical, OTM computable, if there is a program such that if you start it on input n, stops after some ordinal time of steps, number of steps, with the function value as the output, and the subset of omega is OTM computable when there is an OTM program that runs for a while and eventually stops and then has written the characteristic function of that real number on the tape. Okay, so first thing to ask, and this is already quite well known for some time, is what we can compute with an ordinal Turing machine without ordinal parameters. So there is a result by Peter Köpke, Benjamin Seifert, and Philipp Schlicht saying that there is an ordinal eta such that X is OTM computable if and only if it is an element of L eta, and eta happens to be the supremum of the parameter-free OTM halting times. So they take all the parameter-free programs, let them run, some of them will halt, some of them won't. You take the supremum of the halting times of those which halt, this is eta, and this characterizes the computable reals. We can further characterize this eta, namely say that an ordinal is sigma 1 fixed if a certain sigma 1 formula first becomes true in L alpha, and then when you take the supremum of the sigma 1 fixed ordinals, this happens to be eta, also known as the first sigma 1 stable ordinal. And you can also relativize that, but that's not so important for us here. So when you add parameters, then the picture considerably changes. There's a result by Peter Köpke saying that a set of ordinal numbers is OTM computable with ordinal parameters if and only if it is an element of the constructible universe, and this can be relativized as well. So when you in some canonical way encode sets as sets of ordinals, you can say ordinal Turing machines with parameters compute all of L. In particular, there's a certain parameter-free machine that never stops, just runs and runs and runs, and eventually writes every element of L on the tape, or a code for it, you might say. So, so this is computability, and as I said in the beginning, computability is restricted to the constructible universe. But fortunately, there is another notion related or associated with infinitary machines, namely recognizability. In the classical case, for Turing computability, recognizability doesn't make sense, but for infinitary machines it does. So let's see what it is. A set of ordinals is recognizable if and only if there is a program such that when you run it with any set of ordinals as the input, stops and tells you whether the set that you gave it as an input is X. So that's recognizable. You can see if the object that you observe is equal to X. So let us denote by rec alpha the set of real numbers that are recognizable in the parameter alpha, and by rec infinity those that are recognizable relative to any parameter, and by rec we just mean rec 0, rec empty set. So now when you don't have parameters, then recognizability doesn't get you out of L. This is basically a consequence of Schoenfeld absoluteness, which I don't want to go into detail now. It's rather easy to see. It's this recognizes X is sigma 1, 2, and therefore it's absolute. So if there is such an X, it must be in L. But in general, we can ask what the connection between recognizability and computability is. Computability, the ability of some program to write that thing on the tape. Recognizability, the ability of some program to identify whether the thing on the tape is that object. Well, I mean, clearly, if something is computable, then it is recognizable. Just compute it and compare it bit by bit to the oracle. That's easy. But what about the converse? So this we will consider below, but for the moment we fix a very nice way to denote things that are recognizable but not computable, due to Joel Hampkins, who first observed that this phenomenon occurs for infinite time Turing machines. Namely, we call such a thing a lost melody. And so the idea behind is you have heard a certain melody, you still somehow have it in mind. You can't whistle it, but when you hear it, oh yeah, I know this is the melody I had in mind. Yeah. Okay. Fine. In the parameter-free case, we can characterize the recognizables easily. Namely, so there is it's just the reals that are in L eta. L eta is the ordinal I described above. So this means that when you don't allow ordinal parameters, then recognizability is the same as computability is the same as L eta. much more interesting is what happens when you allow arbitrary ordinal parameters. And we will see that in general this can go far beyond L. But first let us note that this set is attractive in the sense that it is conceptually robust. Let's say, give two instances of that of this claim. First, it is stable under constructible equivalence. Yeah. If y and x are constructibly equivalent, so x is in L of y and y is in L of x, then they are either both in here or they are both not in there.
Are x and y sets of ordinals?
Real numbers currently. It doesn't really matter, but I focus on real numbers because that makes certain things a bit less messy.
If you take a real,
yeah,
L of x, it has a definable well ordering.
Yeah, depending on x. Yeah.
Yeah, but x is a subset of the natural.
Yeah, right.
Automatically ordering.
Right.
Okay. Yeah. So you can search in this.
Right. And that's somehow the point, yeah. It's important. Okay. One more instance of this robustness phenomenon. We say that a set is semi-recognizable if there is a machine that only halts when the oracle is x. And we say it is anti-recognizable when there is a machine that only doesn't halt when the oracle is x. And it turns out that recognizability, semi-recognizability, and anti-recognizability are all equivalent for parameter OTMs. So we have quite a degree of robustness. Okay, good. Let's first observe somehow the obvious. If V is equal to L, then rec infinity is just a set of constructible rings. Why is that? I told you before that all sets in here are computable, and all computable sets are recognizable. So, in this case, everything.
So if V is L, then why do you have L there?
Is that meant to be L theta?
No.
It's just V of omega.
Okay, yeah, you can say so, right. Okay, that's true. But I mean, it doesn't hurt having it again. But you're right. It's the class of constructible. It's a set of constructible ordinals. Second, when you add a cone real over L, then you do not add any recognizable reals. That's not too hard to see because if a certain program P in the oracle X stops and X is generic, then this must be forced by some condition. But then you take another cone real which extends that condition but disagrees with X somewhere, and this also, and then P in this oracle also converges to 1, and therefore X is not recognized because the program says yes for another real. So we can note at this point that the claim that every real number is recognizable is independent of ZFC. Fine. Computability, of course, can be relativized, computable from an oracle. And the same is true for recognizability. So let's say you have two subsets of an ordinal. Then we say that X is recognizable from Y in a parameter if and only if there is a program P such that whenever you take a subset of alpha and run P in the oracle Z join Y, where join is just any natural way to encode the information contained both in Z and Y. So for real numbers, you would say place X at the even bits and Y at the odd bits or something. Okay, then this converges to delta ZX, where this is the Kronecker symbol. So intuitively, that means Y helps you in recognizing X. And from now on, we will focus on real numbers. So let me tell you at this point that recognizability from something that is recognizable, computability from something that's computable, that is again computable. The same is not true for recognizability, which somehow makes sense. I cannot recognize a radioactive stone, but I can recognize a Geiger counter, and with that I can recognize a radioactive stone. And the phenomenon is similarly here. Let us denote the closure of the empty set under relative recognizability without parameters by C, with parameter alpha by C alpha, and with arbitrary parameters by C infinity. Yeah, so closure means take the recognizables, take the stuff that is recognizable from the recognizables, take the stuff that is recognizable from that, and so on.
Question?
Yeah.
Relative recognizability with arbitrary parameter. Can you change the parameter when making the second step?
Yes. I mean, for rec infinity, you may. Yeah. Okay. So we will see below that this relation is not necessarily transitive, where not necessarily means it is independent of ZFC whether it is transitive. But in the interesting cases, the recognizable closure does actually differ from the Maier set of recognizables. It is, however, almost transitive in the followings, in the sense that more than 2 iterations do not make sense. They do not increase the set. And in fact, the second reduction can be made very simple. So the following holds. If A belongs to the recognizable closure in any of the senses above, then there is a recognizable set B, a real number B, such that A is primitive recursive in B. So yeah, 2 steps are sufficient. Quite easy reason. Why is that? So suppose that you have a set of relative sequence of reductions of A to C. Yeah, so C is recognizable, xn minus 1 is recognizable from C, and so on downwards to A. And suppose that Pi is a program that recognizes xi from xi plus 1. Then you just define B as the join of this whole sequence. And now the B is recognizable. You look at the last component, that's recognizable by assumption. If that happens to be C, you go on, otherwise you say no, because you already know that can't be B. Okay. Then you look at the second last component and apply Pn minus 1 and see whether it is recognized from Xn and so on, and by this you can recognize B. But obviously X0 is just a component of B. Yeah, so it's primitive recursive. Okay. So now our next goal is to determine what these recognizable closures are. Again, the parameter-free case is rather simple. We saw above that the recognizables coincide with the computables when we don't have parameters, and the computables are certainly closed under primitive recursion, so again, the reals in L eta are the recognizable closure. So, but what when we allow OTMs, what when we allow parameters? So I think, if I look at the time, I can skip at least this. Maybe I take it for granted that you know what Wooding cardinals are, so I skip this. So it turns out that when we allow parameters, then recognizability has a connection to large cardinal principles. And let me first give you the first indication of this. Namely, O sharp is OTM recognizable, given that it exists, in the parameter alpha, if and only if alpha is at least omega 1. So let's ignore this part at the moment, but let's see that, I will give a proof that O sharp is recognizable from omega 1. Just give you an idea how this works. First, O sharp is absolute between transitive models of Z minus that contain omega 1. So if you are given some real number x in the oracle and you want to determine whether that is O sharp, then you first, you have the parameter omega 1, or you have the parameter alpha, which is at least omega 1. You start computing L alpha relativized to x, and you do that until you reach the first L alpha x, which is a model of ZF minus where alpha is bigger than omega 1.
ZF minus is?
ZF without the power set axiom. So, and then you have basically written L alpha relativized to x on the tape, and when that is written on the tape, you can just evaluate truth predicates by exhaustive searching. Yeah, if you have some quantifier running over this, you can just run through the structure and search for a witness or search for a counterexample. So you can evaluate truth predicates on structures that you have written on the tape. So you can just check whether this structure believes that the oracle is equal to O sharp, and the structure will be right because of the absoluteness. And in this way, you can check whether the oracle is equal to O sharp. So as a corollary, we know that it is independent of ZFC whether for parameter OTMs there are lost melodies, because certainly O sharp is not in L, so O sharp is not computable. So L O sharp believes that there are lost melodies, and on the other hand, we have seen above that L, if V is equal to L, certainly there are not any lost melodies. No, this should be computable actually. Second observation concerning this, in L O sharp, omega 1 L is countable, so certainly L O sharp contains a real R that is cone generic over L, and thus a real that is not recognizable. But this R, this cone generic over L, is certainly computable from O sharp because it is an element of L O sharp, and therefore it is also recognizable from O sharp. So we have the following reductions. R is recognizable from O sharp, and O sharp is recognizable from 0, but R is not recognizable, so it is not recognizable from 0. And so if O sharp exists, then relativized recognizability is not transitive. Now we have a counterexample to that. Okay, let's consider for a minute recognizability relative to various different parameters. So we have at least the following consistency result. It's consistent with ZFC that for all countable ordinals, there is a real which is recognizable from Aleph alpha plus 1, but not from Aleph alpha. So let's see how this works. So you have we borrow a certain notion from classical computability, namely the jump. So usually jump contains the indices of programs that compute something and stop. So the recognizable jump in analogy is the set of programs that recognize something. And the alpha jump, J alpha, is now the set of OTM programs that recognize some real number in the parameter alpha. Now this is just a real number. Now, quite analogously to the way that you show that the halting problem is not solvable, you can show that J alpha is never recognizable in the parameter alpha. Classical diagonalization, you may say. And okay, so this does not depend on anything. But now, suppose that V is equal to L, then we can show that J Aleph alpha is recognizable in the parameter Aleph alpha plus 1, which is sufficient because we already saw it can be recognizable in the parameter Aleph alpha. So, how does this work? Well, first, from Aleph alpha plus 1, OTM compute Aleph alpha and L Aleph alpha plus 1. So now you have that written on the tape. Now Aleph alpha can be marked. You can see what Aleph alpha is because that is the largest cardinal in L Aleph alpha plus 1. So you just search through the structure, look for the largest cardinal. There you have Aleph alpha. Now an OTM program with oracle with parameter Aleph alpha cannot run for more than Aleph alpha plus 1 many steps. So either it stops in L Aleph alpha plus 1 or it never stops. So having that structure on the tape allows you to solve the halting problem for OTMs that have parameter Aleph alpha. And but now you can simply compute the recognizable jump of Aleph alpha. How do you do this? You just, when you have a certain program P, and you want to know whether this recognizes something in Aleph alpha, what do? I mean, you have L Aleph alpha plus 1 on the tape, so you certainly have all constructible ordinals on the tape. So you just run through them. For each of them, you look whether the program stops. If it doesn't stop for any real, then certainly the program doesn't belong in the jump. And if it does stop, well, then you check whether there is exactly one real where it says yes, while it says no for every other real, and if so, you put, then it belongs to the recognizable jump, otherwise it doesn't. Okay, and that's the idea. Okay. So, the really tough question is then, what is C infinity? So C infinity, I remind you, is the recognizable closure of the empty set with parameter OTMs. Okay. Maybe this is not a very good question. We have already seen that this is highly non-absolute. For example, it could be L. So maybe a better question is then, what can the recognizable closure be? In particular, is there an upper bound? What is the recognizable closure when the universe is as large as possible? And this is what we are trying to determine now. So the largeness assumptions we make is that there is an omega sound omega 1 plus 1 iterable pre-mouse with a top measure above a Woodin cardinal and projectum omega, ultimate projectum omega. Such a pre-mouse, if it exists, is unique, and it is called M1 sharp. If you think that this is a somewhat strange assumption, don't see where it leads. Maybe a bit more familiar is that you get the existence of such a pre-mouse if you assume that in the real world there is a measurable cardinal above a Woodin cardinal. So you can also say we are working under this assumption. So from M1 sharp, we get another structure called M1 by taking the top measure of this measurable cardinal above the Woodin cardinal and iterating it and iterating it and iterating it n many times until it is gone. Yeah, so called iterating it out of the universe, and the object that you get in this way is M1. Okay. Now let's connect this with computability. I mean, M1 that's a kind of canonical inner model for a Woodin cardinal. And here's our result. If M1 sharp exists, then the recognizable closure, only talking about real numbers, of the empty set under parameter OTM recognizability is the set of reals in M1. And if you prefer it shorter, C infinity is the set of reals in M1. Okay. Let's see how this is proved. It's somehow lengthy proof, but at least I can give you an idea how this works. So first, let's see that the recognizable closure does indeed belong to M1. This is, you could say, this is somewhat easy, this direction, modulo a miracle. The miracle is called Woodin's genericity iteration. So this is a theorem, you could guess, due to Woodin, which says that in M1 there is a countable partial order such that if a real number is not in M1, then there is a countable iterate n of M1 such that x is generic over the image under the iteration embedding of that partial ordering over n. Yeah, so you iterate, and there are never any cutbacks, so the iteration, so the embedding exists in the end, and then you take the image of the original partial ordering, and for this partial ordering in n, the x is generic. Okay, that's the genericity iteration. And okay, how do we use it? Suppose that P recognizes the real number x in the parameter beta, and suppose that x is not an element of M1. Okay, we use a genericity iteration, iterate, and we get some n such that x is generic over n, and since the iteration was countable and the q was countable to begin with, this partial ordering will still be countable. So, by absoluteness of computations, when you take the generic extension of n by x, or extend n by x, then this extension will believe that P in the oracle x and the parameter beta converges to 1. Yeah, I mean, computations work just the same in all transitive models of ZFC, very explicitly definable. So this model believes that P says yes to x in the parameter beta. Okay. So since this is a forcing extension, there is some name for x, and so by the forcing theorem, there must be some condition that forces that p, when run in this oracle, converges to 1. Now, if p would decide every bit of x, then x would be definable in n. You know, we're just saying it is that real number whose bits are decided by p. So then it would be an element of n, but the iteration does not add any real numbers, so it would already be in M1, and this would contradict our assumption. Okay, so this means that p does not decide every condition of every bit of x, so there must be two strengthenings, q and r of p, and some bit such that q and r disagree on the kth bit. So let's say q believes that the kth bit of x should be 1, and r believes that it should be 0. Okay. Suppose that in reality the kth bit of x is 1, so that r gets it wrong. Then since the partial ordering with which we are working is countable, there is a generic filter over the extension that contains r. But now when we evaluate x according to that filter, then this extension will believe that p, oh here the beta is missing, that p in the oracle y also converges and says 1. Okay, but that's bad, yeah? I mean, this means the program says yes to y, and y differs from x. And p was supposed to recognize x, so only say yes to x. So that means first that inside nxg, py in the parameter beta halts with output 1, while y is not equal to x, which is not what should happen. But since computations are absolute, this means that p in the oracle y and the parameter beta also halts with output 1 in the real world. And now you have a contradiction to the assumption that p recognizes x. Okay, so that's one direction. Let's look at the other direction, that the reals m and 1 actually do belong to the recognizable closure. So the idea is here, if x is m and 1, then there must be some m1 countable ordinal m alpha, so that alpha belongs to the alpha stage of m1. And I mean, by going a bit higher, if we want to, we can also assume that m1 alpha is sound and has ultimate projectum omega. Now there is a theorem of Steele which says that m1 alpha is then uniquely characterized as a sound premouse of height alpha that has ultimate projectum omega and is pi12 iterable, where pi12 iterability is certain, let's say, weakening of full iterability of a premouse. So now how do we go on from here? I mean, the point is m1 alpha becomes countable at the next stage because it has projectum omega. So there is a real number at the next stage that codes m1 alpha. And now we want to use this characterization to recognize one of these codes. And of course, then from the code for the whole structure that contains x, we can reobtain x. Yeah, that's the idea. Okay, so first, m1 alpha has ultimate projectum omega, so the next stage will contain a bijection from omega to m1 alpha. And therefore, there is a real number that codes m1 alpha. For example, in the following sense, you take the set of pairs of natural numbers such that the image of the first element is an element of the image of the second element. But that's just one way to code a countable structure into a real. Okay. So let's say that y is in the canonical well ordering of m1 the minimal real that codes m1 alpha together with the extender sequence up to that stage. So claim is that this y, this minimal code, is OTM recognizable in the parameters alpha, which I remind you was the height of the premouse, and omega 1. So since we are only allowed to use one parameter, we take the Cantor pair. So at first, it is just a question of, an OTM can test whether a given real code is a well-founded structure, basically by just exhaustively searching for an infinite descending epsilon sequence. And it can also evaluate first-order predicates, so it can test whether a given real code is a well-founded structure of this form. It's also not hard to test whether the code has projectum omega and whether it is a code of a sound structure. So when that is true, we can test whether Y is a minimal code for the structure it codes by just, let's say, computing one further L stage. Then you get some codes of the structure below because the projectum was omega. Searching through the next stage and seeing whether there is a smaller code. So in this way you can know whether the code is minimal. And so the last thing to check is pi12 iterability, but pi12 iterability has its name because for countable structures it's pi12, and OTMs have the nice property that when they're given the parameter omega 1, they can test pi12 statements, basically in the way that with the trick that we used above to identify O sharp. And so therefore we can recognize Y. But since Y codes the whole structure which contains X, in Y the real number X is coded by some integer, and therefore X is in fact OTM computable from Y, just as the element coded by 37 or something. And therefore it is certainly recognizable from Y. So it's computable from something that is recognizable, and then it is in a recognizable closure. And so we have X in C infinity. So this finishes the proof that the reals in M1 can be characterized as the reals in the recognizable closure. Okay. We can try to extend this to arbitrary. Next question would of course be, what if we don't look at real numbers, but if we look at subsets of arbitrary ordinals? This becomes much harder, but okay, for subsets of countable ordinals, we still have a result, namely the following. When you take the first measurable cardinal in M1, and you take a normal ultrafilter on that cardinal, and say that M alpha is the alphath iterate with that ultrafilter, and take the intersection of all these iterates, which we call M infinity. Then by a somewhat similar argument to the one I just presented, with just some little extra subtleties, we get that if alpha is a countable ordinal and X is a POTM recognizable subset of alpha, then we have X in M infinity, and of course M infinity is closed under OTM computability, and therefore we have a characterization of the recognizable closure there as well. If we go to the general case, subsets of arbitrary ordinals, we have at least a wealth of characterizations of that set given by the following theorem. So if you have a subset of alpha, and we want to characterize when does X belong to the recognizable closure, and remind you, being in the recognizable closure means being OTM computable from something that is recognizable. Okay. So the following are equivalent. X is a POTM computable from some subset of alpha that is first POTM recognizable. That is parameter OTM recognizable. So this means belongs to the recognizable closure. Second, there is a sigma 1 formula, phi, and an ordinal beta, such that Y is unique with the property that L with Y believes that phi of Y beta. So it is sigma 1 definable with an ordinal parameter in Ly. Third, you actually can drop the sigma 1 condition. There is just any formula such that y is a unique witness of phi y beta in Ly. Another characterization is implicit definability. I think this notion is due to Joel Hampkins, is that right? Yeah. Which means that now, I mean, you still characterize y uniquely as a unique witness to some formula, but now you don't get to add y to L, you just have it as an extra predicate. In this way it is uniquely definable. And finally we have a characterization as being a definable subset of alpha in this language, L alpha ON0, which means that you take atomic statements of the form gamma belongs to y, where gamma is some ordinal below alpha, and you take the negations and then you close that under infinitary conjunctions and disjunctions, and when you take and being characterizable by such an expression that lies in L is another characterization of this notion of belonging to the recognizable closure. Okay, here is some other idea. I mean, so far we have only talked about sets of ordinals, but of course there is a rather natural way in which sets of ordinals can be seen as codes for just any set, and vice versa. For example, you can do the following. If you have a set of ordinals, then define the decoding of this set as follows. First, interpret every element, every ordinal in A as a pair of ordinals, a pair alpha beta. And then for every first component that shows up, look at the set of second components. By recursion, you regard this as a code for some set. Okay, the set of betas that occur as a second element of a pair whose first element is alpha. And then this decoded set gets into the decoding of alpha. And this you do with all first components, and then you just get some set. In this way you can decode any sets of ordinals, and via well ordering a set and playing this trick backwards, or via well ordering the transitive closure of some set and doing this trick backwards, every set has such a code. So we can also talk about recognizing arbitrary sets, you might say, or having a recognizable code. Okay, but now of course the interesting question is what happens if we take the whole recognizable closure and decode that? What do we get? Okay, let's say this is R. So R is the class of decodings of recognizable sets of sets of ordinals that belong to the recognizable closure. So here's a theorem about that. If you do that in some transitive class modulo ZFC, then at least we know the following things about R. It's a transitive class which contains all ordinals. It's closed under joins and relativized constructibility. So if there are two sets of ordinals in there, then that join is also in there. Every element of Rm has a well ordering in Rm. And from this you also get that the axiom of choice holds in Rm. So from this you already get that this Rm is a model of the existence axiom, the axiom of its extensionality because it's transitive, of infinity because it contains omega, of delta zero separation because it's constructively closed, of union, pairing, foundation, and the axiom of choice. And moreover, it is stable in the sense that, I dropped the m's, because that would make it completely unreadable. But if you form R inside R, you get R back. So in this sense, this class of decodings is stable. Okay, so conclusion would be that we have started with a certain notion of computability, that when you just look at computable sets, you remain inside L, which I called the constructible barrier in the beginning of the talk. But in a quite natural way, by looking at recognizability instead of computability, we have obtained structures that lie far beyond L, inner models for Houdin cardinals, for example. So I think the conclusion would be, also for set theorists, set theorists interested in large cardinals, it makes quite a lot of sense to look at these models because this constructible barrier apparently can be overcome. So, yeah, here are some ideas for further results, or some further questions. First, what is this R? I mean, this class of decodings of sets of ordinals in the recognizable closure. We have, I think yesterday, we found out that it is in general not a model of sigma 3 replacement, so it is not a model of ZFC, but it could be a model of something sensible. Yeah, for example, it could be a model of Kripke-Platek set theory. We don't know. Then we could look at consequences of the statement that every set belongs to the recognizable closure, or every set is recognizable, meaning sets of ordinal numbers. Yeah, you could say this is a kind of expression of definabilism and relates to the statement that everything is computable. Then we do not know what happens when we start with a weaker assumption. Yeah, I mean, a measurable above a Woodin cardinal is already quite strong, and maybe if we assume less, we can characterize other inner models in a computable way. Then a way of further strengthening the notion would be that instead of single parameters, we allow, for example, countable sets of ordinal parameters. Of course, that trivializes the question with respect to real numbers because they are just parameters. But still, if you look at arbitrary sets of ordinals, that probably will increase the strength a lot. We have no idea so far what happens then. And finally, Juliet Kennedy, Menachem Makido, and Yoko Venen have for a while been studying L, where they replace L means iterate first order definability, and they have looked at what happens when we replace first order with something else, like some infinitary logic or second order logic or something. And in this way they have obtained certain alternative L's with a stronger background logic. Now, since this idea of iterating something stronger than first order definability seems to relate to this idea of generalized computation, it would be nice to see whether we can get computable characterization of these alternatives else, or whether there are some other connections. Okay, yeah, I thank you for your attention.
Right question. So my understanding is that that once you have parameters, the distinction would be between saying yes, this is my input, saying no, this is not my input, or saying yes, this is, or no, this is not. So is not going to be there, because you can kind of just wait longer and see whether the other one would have stopped, right?
Oh yeah, okay.
Which of these notions actually is the most natural one? If you say if you wanted to look at situations where your parameters are bounded, so you can't just wait longer.
Okay, I mean, the original notion is the machine always has to stop and say yes or no, and I would still think that this is the most natural way to go about it. Yeah, you are presented with some object and you are supposed to say yes or no. I mean, these alternative characterizations with semi-recognizable and anti-recognizable, I think they are somewhat nice because they show that with arbitrary parameters this becomes very robust. But let's say if you steal my possibility to do this, then I would go back to the original definition and say the machine should always have an answer.
The recognizable things can be naturally well ordered, correctly?
because you well order the programs, the ordinals, and so on.
Yep.
So what kind of well ordering is that? What complexity?
Okay, I mean, what you would want to say is that, I mean, okay, you have to order it some way, let's say, first by the program and then by the parameter. So we'd say x is smaller than y if the first program, so if the smallest, lexicographically smallest pair program ordinal that recognizes x is smaller than the lexicographically first pair q beta that recognizes y, yeah? Okay. I'm not sure, I think
Okay, but there's the question of that you have to quantify over not just the programs, but about the running of the program. So it's even for reals, it gets very far out of descriptive set theory.
Of course, yeah.
Oh, yeah.
I mean,
Does that relate in any way to the ordering of the reals on M1? I mean, is it?
seems sensible. I haven't checked, yeah. Something to consider, yeah.
Scott and McCarthy, is it a recursive definition of ordered pair, and each L alpha is alpha infinite is closed unquote, and I just wondered whether that would be useful in your decoding.
Okay, I mean, I didn't even know about it until, so I just thought about the first thing that came to my mind, how to encode sets and sets of ordinals. But okay, if that is a good way to do it, I can have a look at it.
It's rudimentary recursive in my sense.
Aha, okay. Okay, but I mean, I see. But I mean, okay, this encoding is quite nice. Yeah, I mean, for example, like whether two sets code the same set is decidable and everything. So whether one coded set is an element of another coded set is decidable given the code. So it really basically does everything that you would want.
Other questions? Well, in which case we thank the speaker again.